This is a compression spring and it is designed to take load like this in compression. But in this video, we are going to learn how to use this same compression spring under tension. Of course, not directly like this. This doesn't work effectively this way. Compression springs are designed to only compress, not to stretch. And I promise I'm not going to stretch it at all. So how it is possible to use this compression spring under tension loading without stretching it? But before we get to that, you might thinking, why do we even need to learn to use a compression spring under tension loading? Why not just use a tension spring for tension loading? Tension springs are also readily available with almost the same cost. So yes, you are right. In most of case, for compression loading applications, I use compression spring. And for tension loading applications, I use tension spring. Simple. But in my experience, in some certain tension loading applications, tension springs doesn't perform well because of their three major drawbacks. And those drawbacks can be completely eliminated by using a compression spring instead of tension spring. This video is sponsored by Brilliant. More about them towards the end of the show. First drawback of any tension spring is having no safety limit. A compression spring in its initial condition has open coils. There are clear spaces between them. When we start compressing it by increasing the load, the space between the coils start reducing. And when we fully compress it, all the coils touch each other and the spring becomes solid. Now, even if we increase the load further, let's say 2 times, 3 times, even 10 times, nothing happens. The spring is safe because it's already become solid. Now let's take a tension spring. In its initial condition, the coils are already closed, exactly opposite to compression spring. Now when we apply load, the coils begin to separate and we can continue stretching it up to its maximum allowable deflection. The maximum allowable deflection is determined by a spring's material elastic yield limit. But here is the problem. In tension spring, there is no mechanical stop, unlike a compression spring. So we are able to continue stretching it further if we want. But once we stretch it beyond its maximum allowable deflection, the spring material elastic yield limit will cross and permanent deformation will start. And that is the first drawback of any tension spring. You must ensure the maximum load always stay within allowable limit. If any sudden load is applied that exceeds the maximum allowable force, the tension spring will start losing its spring function and may get permanently damaged as well. Whereas a compression spring doesn't get damaged under sudden overloading, even if the load becomes several times higher than its rated reaction capacity, because it simply becomes solid. Now, the second drawback of a tension spring is lower allowable deflection. For a standard round wire compression spring, the allowable deflection is usually about 40 to 45% of its free length. And for special shapes like rectangular wire ultra deflection compression springs, the allowable deflection can go up to 60-65%. So what does this mean? Let's understand it with an example. Let's say we have a round wire compression spring with a free length of 100 mm and having 40% allowable deflection. So if we compress it fully to its solid length, the deflection will be 40% of its total free length. That means 100 into 40%, 40 mm. And the solid length will be 100 minus 40, 60 mm. Now the tension spring. So tension springs have relatively low allowable deflection. usually about 20 to 30% of its free length. And remember, in tension spring, the free length includes hook to hook length. So if we have a tension spring with 100 mm free length, and let's say allowable deflection is 25%, so we can stretch it up to 100 plus 100 into 25%, 125 mm. In some ultra-coil tension springs, allowable deflection may reach to 35%. But even then, it's still nearly half of the ultra-deflection compression springs. But how this large allowable deflection feature actually matters. So let's say we have a tension loading application where we need 20 mm total deflection from a tension spring. So if we have a tension spring with 25% allowable deflection, so the required free length would be about 80 mm. So for this application, we would need at least an 80 mm long tension spring. Now suppose if somehow in this same tension loading application, if we can use a compression spring, then we can have higher allowable deflection. Let's suppose 45% allowable deflection. Then the required free length would be roughly around only 45 mm. That is almost half the length of tension spring. And that's how the higher deflection of springs make the mechanism more compact. Now, the third drawback of a tension spring is this always require an initial amount of force just to start deflecting. We all know the spring reaction force equation. F is equal to minus K into X, where F is a spring reaction force, K is a spring constant, X is the deflection of a spring, and the negative sign simply indicates the reaction force acts opposite to the direction of deflection. The deflection is a displacement vector, so it has a direction. And this equation directly applies to compression springs. So at zero deflection, there is no reaction force. And as the deflection increases, the reaction force increases linearly, all the way up to maximum reaction force at maximum allowable deflection. The graph between the reaction force and deflection is almost linear. But in case of tension spring, this is different. Tension springs are intentionally manufactured with some initial tension. The coils are wound tightly together so they can stay closed at no load condition. So every tension spring first requires an initial force just to separate the coils, and then they start follow the spring force equation. This initial tension is usually about 20 to 30% of the maximum allowable load. For example, this is a data sheet of a tension spring, a spring constant 1.96 Newton per millimeter. The maximum allowable load is 77.47 Newton and the initial tension is 20.59 Newton. This is about 26% of maximum allowable load. Now suppose if we want to extend this spring by 10 mm. So first we must overcome this initial tension of 20.59 Newton. Then for 10 mm deflection, 1.96 into 10. 19.6 Newton. So the total force required will be 20.59 plus 19.6, 40.19 Newton. And this initial tension is required even if we want to deflect the spring by just 1 mm. Whereas in compression spring, no such initial tension is required. Another issue with tension spring is that initial tension can vary even among tension springs of the same size. And because of that variation, accurately estimating the exact reaction force becomes more difficult. But in compression spring, the spring force only depends on a spring constant K. So we can accurately calculate their reaction force. So the difference between a compression spring and a tension spring is not just that they work in opposite direction, But there are these three major advantages of compression springs over the tension spring. So in application where a tension spring is subjected to sudden loading and there is no mechanical dead stop, for safety, I prefer to use compression spring in place of tension spring. Second, in application where I need larger spring deflection in tension loading and we also want a compact mechanism, I use compression spring instead of tension spring. Third, if application require precision, predictable tension force, I use a compression spring instead of tension spring to get proper calculated linear reaction force. Now comes to the main question of this video, main point of this video, how we can use a compression spring in place of a tension spring. So the idea is very simple. I have attached these two ropes to the end of the coils of the compression spring, and now I am passing these ropes through the spring from opposite ends like this. Now something interesting is happening. I'm pulling this rope outwards and it's compressing the compression spring. Here the compression spring is doing exactly what it is designed for, working in compression, but the loading is tension, just like we are stretching a tension spring. And this is how we can use a compression spring in tension loading. This is just an idea. We cannot directly use this arrangement in a machine. The compression spring cannot stay aligned properly. It starts buckling and bending sideways. Another problem is these are just loose ropes. It's not reliable. But we are design engineer. We can convert this simple idea into a workable and robust spring mechanism. But before we jump into CAD designing, first let's finalize the concept properly. First, instead of these loose ropes, we can use something solid, like steel rods, maybe 2-3 mm in diameter, and we can bend the ends of rods into a hook, just like a tension spring hooks. So these can be directly used in place of a tension spring. Now, how do we attach the other ends of the rod to the spring coils? So my first thought is, can we simply weld them to the spring coils? So yes, technically we can, but spring wires are usually very small. Moreover, welding can locally change the heat treatment of the spring and disturb the spring constant K. This is not acceptable. Also, I need these hooks at the center of the compression spring, not on sides. If they are offset, it will create a movement, which is causing uneven deflection in a spring. So the hook must be placed at the center. And to achieve that, we can simply place two round discs at the both end of the spring like this. In this 2D sketch, they look flat rectangular, but imagine them in a circular disc. Now to attach these hook ends to the discs, we have two options. First is we can provide a tappet hole in discs and external thread on the rod's end. I would use at least M3 thread size. As a machine design engineer, I prefer to not go below M3. This is my practical lower limit. You can go down to M2 if required, no issue. Now, since we are using M3 thread size, so the disc thickness should be at least 3 mm. For steel parts, the thread engagement should be minimum 1D. More about that in this video. You can check it out later. Another option we have, we can use a clearance hole in the discs and use a nut on the both sides to fix the rod. Both options are good, but how do we pass these rods through the opposite discs? It's very simple. We can provide clearance hole in the both discs for the rod to pass through. Now, apart from that, we still have two problems. First, the discs are not fixed to the spring, so they can slide anywhere with these hooks. Although we can fix it by adding collars in discs, but it would require additional machining, which increase the cost. Second, these hooks are near the center. The force of action are parallel but not collinear. It's slightly offset. And both problems can be solved with a simple concept modification. We can fix one hook exactly at the center of a spring. And we can redesign the second hook into a U-shape hook, something like this. And both legs will be fixed with the disc. Now, the line of force of action of the both hooks are collinear and exactly centered. And this U-shape hook also help to keep both discs aligned and also preventing the lateral movement of the spring. The spring is stuck in this hook. And now for me, this concept looks perfect. The mechanism is stable, economical, and also reliable. Now, if you look closely, we are not just trying to design the hardwares. We are actually applying the physics and mathematics, geometry to ensure the alignment and stability, while the functions and equations helps us to determine the overall system behavior. It's like math and physics are the true foundation of any mechanical design, and this is why I use Brilliant. I use Brilliant to continuously sharpen my math and physics, so I can improve my real engineering problem-solving ability. Recently, I explored their coordinate geometry and coordinate transformation exercises. What I really like is the direct interaction. I just move the coordinate points, adjust the distance and rotations, and immediately sees how the system responds. And that's immediate feedback builds real institution. And that is not only limited to geometry. If you want to strengthen calculus, quadratics, exponential function, probability, circuit, or even scientific thinking, Brilliance covers all in one single subscription. These exercises are built by the educators from MIT, Harvard, Stanford, and the platform is designed for both kids and adults. So whether you are building your foundation as a student or sharpening your math and physics skills as a professional engineer, the platform adapts your knowledge and pace. So if you want to build strong math skills and think more clearly as an engineer, check out Brilliant. Go to brilliant.org/mastermechanicaldesign or scan the QR code on the screen. If you sign up with my link, you will get 30 days free and 20% off the annual premium subscription with unlimited daily access to everything on Brilliant. The link is in description. And now let's finally design this mechanism. For that, here I have considered this compression spring of free length 100 mm, outer diameter 25 mm, and the wire diameter is 2.2 mm. And now let's design these discs. Let's consider the disc diameter 25 mm, the outer diameter of the spring. Now the thickness of the disc. So since we are using a nut connection between the disc and the hook, so the disc do not need a threaded hole. Simple clearance holes are there. So we can reduce the disc thickness to even 2 or 1.6 mm. Let's consider 1.6 mm. Place it on the both sides. I always assemble the components early. It helps visualize the next step clearly. And now it's time to design the hooks. First, let's design this U-shape hook. And since we are using a M3 nut, the rod diameter must be at least 3 mm. Now here is a problem. If the rods pass through very close to the spring inner side, here this outer nut is fine, but this inner nut, this nut will interfere with the spring. So we can turn down this rod end into a stab and cut the threads on the smaller diameter stab. and use only one nut from outside. This way, the inner side do not need any nut. Now the step diameters become M3. That means the main rod diameter must be larger, let's say 3.5 millimeter. Now this looks perfect in CAD, but if you think like a machinist, there is a hidden problem. These steps and external threads cannot be machined after this U bending. Both operations need to be performed before this bending. So at very first, rod must be straight. Then both ends are turned. Both threads are cut using the die. And then the rod will be bent into a U shape. And the bending will most likely be manual. And if the bending process is manual, the starting phase of the both threaded steps will not lie perfectly in same plane. There can be easily 2-3 millimeter mismatch. This means both steps may not sit flat on the disc together, so one end may not tighten properly. This problem doesn't exist if we keep the full length of threads and use 2 nuts per rod, just like this concept. Even if bending is slightly inaccurate, we can adjust the nut and compensate. But again, the nut and spring will have interference. So as a designer, here I would prefer a small compromise. I will not try to tightly control the spring internal diameter. Instead, I will leave some clearance so I can properly tighten the nut on both sides. Now you might thinking, the spring can shift slightly at another end. So yes, it can slide a little sideways. But this is acceptable as long as it cannot slip off the discs. And we can verify that with calculations. An M3 hex nut is about 6 mm across the outermost side. Means the radius is 3 mm. So we need to maintain this 3 mm clearance between the U-hook center line to the spring inner diameter. The spring inner diameter is 25 mm, the outer diameter of the spring, minus 2 into 2.2, the wire diameter, 20.6 mm. So the center to center distance between the U-hook rods will be 20.6 minus 3 minus 3. 14.6 millimeter. Consider the spring manufacturing variation and let's round it about 14 millimeter. And now we can design this U-hook. So here I have set the center distance 14 mm and the length is about 120 millimeter. We will adjust it later. And the rod diameter 3 millimeter. And set the external thread size M3 and set the length up to 10 mm. Again, we will adjust it later. Now place it in assembly, and to fix it, here we have to add 2 clearance holes in disc. So let's mark the 2 hole positions at 14 mm and add 3.2 or 3.5 mm clearance holes. And now let's finally place the nuts. And here I am using this same disc on another side as well, because there is also the clearance holes at same distance to pass through these rod. Interesting. And now let's check the spring sliding condition. So a spring inner diameter is 20.6 millimeter. Rod center to center distance is 14 millimeter. So the rod outer to outer surface would be 14 plus 3, 17 millimeter. And the gap around the rod outer surface and the spring inner surface would be 20.6 minus 17, 3.6 millimeter total. So the gap on each side is 6.3 divided by 2, 1.8 millimeter. So to prevent the spring from slipping off the disc outer diameter must be extended at least 1.8 millimeter beyond the spring outer diameter all around. So let's increase the disc diameter to 25 plus 1.8 plus 1.8, 28.6 millimeter. Let's consider 29 millimeter. So now even at maximum lateral deflection, the spring cannot slip off the disc. And now let's design this single hook spring, and we will keep the same hook size as U hook. So let's sketch a new part, and let's keep the hook center line diameter 14 mm. So we will get the same inner size and set the length 120 millimeter and the rod diameter 3 millimeter. And let's also add the threaded step at another end M3. And now let's place it in assembly. And now we also need to provide a clearance hole in disc for this hook. Let's do it. Let's make the clearance hole 3.2 millimeter in center. And let's also put the two nuts on the both sides. And now we can adjust the hook lengths as per the requirements. And this is it. And now this is not a compression spring anymore. It's a tension spring with all benefit of compression spring. This tension spring has end mechanical limit. This has ultra deflection and also no need of initial force to deflect. And let me clearly say, this design is not my patent or original invention. You can find this similar mechanism in market, commonly known as hanger spring. But the problem is most designers don't know about it. And even those who know about it often do not fully understand the engineering benefits of this spring and when it is actually needed in application. And to fully understand it, I have explained in Nolan style, reverse storytelling. But the main goal of this video was to give you a perfect example of a step-by-step designing process, where we started with a simple idea. We convert that idea into a practical and robust mechanism concept, and then we designed it for manufacturing. And this is it for this video. I hope this video will help you to improve your designing workflow. If it did, please give it a like. Also, don't forget to check out Brilliant. The link is in video description. And thank you so much for watching this video.